A pleasant election day, everyone. Welcome to Group 2, and we will be discussing the distribution of measurements and results. These are the members of my team: Ayan Mercurio, Crystal Kiboyen, Kimberly Pantua, Sweden Usop, Kristen Mayor Desio, and Juliana Dumagas. These are our subtopics. First, populations and samples. Second, probability distributions for populations. Next, the binomial distribution, the normal distribution, confidence intervals for populations, probability distributions for samples, samples distributions and the central limit theorem, degrees of freedom, confidence intervals for samples, and a cautionary statement.
Good day. For our first subtopic, it is all about the populations and samples. In this table, it shows the result for two determination of the mass of a circulating US penny. For the first experiment, the mass or gram of penny number 1 is 3.080, number 2 is 3.094, number 3 is 3.107, number 4 is 3.056, number 5 is 3.112, number 6 is 3.174, and number 7 is 3.198. Over x is equals to 3.117. The chemical balance is equal to 0.051. For the second experiment, the mass of penny number 1 is 3.052, number 2 is 3.141, number 3 is 3.083, number 4 is 3.083, and number 5 is 3.048 over x of 3.081 and the chemical balance of 0.037. Populations and samples. A population is a set of all objects in the system we are investigating. This population is so large that we cannot analyze every member of the population. Instead, we select and analyze a limited subset or sample of the population.
To predict the properties of a population based on a sample, it is necessary to know something about the population's expected distribution around its central value. The distribution of a population can be represented by plotting the frequency of occurrence of individual values as a function of the values themselves. Such plots are called probability distributions. Unfortunately, we are rarely able to calculate the exact probability distribution for a chemical system. In fact, the probability of distribution can take any shape depending on the nature of the chemical system being investigated. Fortunately, many chemical systems display one of several common probability distributions. Two of these distributions, the binomial distribution and the normal distribution, are discussed next.
Hello, good day. I am IMP Mercor from BSMT1B, and I am about to discuss the subtopic of binomial distribution. So, the binomial distribution described as a population in which the results of numbers of times particular event occurs during a fixed number of trials. So, P of x and n equals to the factorial of n over to the factorial of x times to the factorial of n minus x times p to the power of x times 1 minus p to the power of nx. So the factorial denoted by the exclamation mark, and the factorial means the multiply by decreasing positive integers. For example, 5 to the factorial of 5. So the factorial of 5 is equals to 5 times 4 times 3 times 2 times 1 is equals to 120. So the binomial distribution is P is the probability of success of any trials. So the Q is equals to 1 minus P is the probability of failure, and N is the number of trials of experiments, and the X is the number of successes. It can take the value of 0, 1, 2, 3, and so on and so forth. So the NCX is equals to the factorial of n over to the factorial of x times n minus x, and denotes the number of combination of n elements taken x at the time. Binomial distribution is the summarize of trials or observation when each trial has same probability of attaining or attempting one particular value. So the binomial distribution determines the probability of observing specified numbers of successful outcomes in specified numbers of trials. So what does a binomial formula do? So binomial distribution formula allows us to compute the probability of observing specified numbers of successes. So when it the process repeats specific numbers at the time. For examples, in a set of patient, in the outcomes for given patient either successful or failure. So, binomial distribution, just a remind that the symbol of exclamation mark is after the number means the factorial. So, the factorial of non-negative integers x is denoted by the x, factorial of x, and the factorial of x is the product of all positive integers less than or equal to x. For examples, the factorial of 4. So 4 is factorial of 4 is equals to 4 times 3 times 2 times 1 is equal to 24. So for example, let's say that 80% of all business startup in IT industry report that that they generate a profit of their first year. So if a sample of 10 new IT business startup is selected, find the probability that exact 7 will generate a profit of their profit in the first year. So the binomial distribution, there are only two possible mutually exclusive outcomes. So generate a profit of first year or not. So yes or no. So it yes. There are fixed number of trials of startup. Also that's it's 10. So the IT startup is independent and reasonable to assume that this is true. So the probability of success of each startup is 0.80. Then we know that the n is equals to 10 and the p is equal to 0.80 and q is equal to 0.20 and x is equals to 7. So the probability of 7 startup to generate a profit in their first year is p of x is equals to 7 equals to the factorial of 10 over to the factorial of 7 times to the factorial of 10 minus 7 and times to 0.80 to the power of 7 and times to 1 minus 0.80 to the power of 10 minus 7. So the binomial distribution is this is equivalent to p of x equal to 7 has the result of 0.2013. So there is a 20.13% probability that exact 7 of 10 IT startup will generate a profit of first year when the probability of profit in the first year of each startup is 80%. So the binomial distribution will define the measure of central tendency and spread. The expected mean value is the mean equals to NP, and the expected spread of given by the variance is the variance equals to the NP times 1 minus P, or the standard deviation of square root of NP times 1 minus P. So the binomial distribution describes the population whose member has only specific discrete value. So that's for the subtopic for binomial distribution. Thank you.
Normal distribution is also known as the Gaussian distribution. It's a probability distribution that is symmetric about the mean, showing that data near the mean are more frequent in occurrence than data far from the mean. In graph form, normal distribution will appear as a bell curve. One reason the normal distribution is important is that many psychological and educational variables are distributed approximately normally. Measures of reading ability, introversion, job satisfaction, and memory are among the many psychological variables approximately normally distributed. Normal distribution have k characteristics that are easy to spot in graphs. Mean, median, and mode are exactly the same. The distribution can be described by two values, the mean and the standard deviation. The standard deviation stretches or squeezes the curve, a small standard deviation a narrow curve, while a large standard deviation leads to a wide curve. Where in that picture, there are three colors which shows the normal curve or mesocortic, platycortic, and leptocortic. Formula of the normal curve, f of x equals to 1 over standard deviation square root of 2 pi x e raised to negative quantity of the square of x minus mean all over 2 times variance. Normal curve, also called the z-distribution, is a special distribution where the mean is 0 and the standard deviation is 1. Z-score formula normal distribution, z is equals to the difference of x and mean over standard deviation, where x is an individual value, u is the mean, and O for standard deviation. Z-score is associated with a probability or p-value that tells you the likelihood of the values below the z-score occurring. Using the z-distribution, to find the probability of such scores in your sample exceeding 1,380, you first find the z-score. The mean of our distribution is 1,150 and the standard deviation is 150. The z-score tells you how many standard deviations away 1,380 is from the mean. Z is equals to 1,380 minus 1,150 divided by 150 is equals to 1.53. This is the probability of such scores being 1,380 or less, 93.7%, and its area under the curve left or the shaded area. To find the shaded area, you take away 0.937 from 1, which is the total area under the curve. Probability of x less 1,380 equals 1 minus 0.937 equals 0.063. That means it is likely that only 6.3% of such scores in your sample exceed 1,380.
Values reported in this fashion are called confidence intervals. Equation 4.4, 24.4.2, for example, is the confidence interval for a single member of population. Table 4.4.2 gives the confidence interval for several values of z. For reasons that will be discussed later in the chapter, a 95% confidence level is a common choice in analytical chemistry. Example: what is the 95% confidence interval for the amount of aspirin in a single analgesic tablet drawn from a which population for which true mean value is 250 mg and for which population standard deviation is 5? Thus, we expect that 95% of the tablets in the population will contain between 240 and 260 mg of aspirin. We collect n samples drawn from a population of known population standard deviation and report the mean. The standard deviation of the mean, population standard deviation raw score minus population standard deviation of the sample mean, which also is known as the standard error of the mean. Population standard deviation of sample mean is equal to population standard deviation over square root of sample size. The confidence interval for the population mean, therefore, is population mean is equal to the sample mean plus minus sign score of population standard deviation over square root of sample size. An analysis of 7 aspirin tablets from a population known to have a standard deviation of 5 give the following result in milligram aspirin tablet. So we have 246, 249, 255, 251, 251, 247, and 250. So, what is the 95% interval for the population expected mean? The mean is 249.9 mg aspirin per tablet for this sample of 7 tablets. For a 95% confidence interval, the value of z is 1.96, which makes the confidence interval 249 plus minus 1.96 times 5 over square root of 7 equal to 249.9 plus minus 3.7 almost equal to 250 milligram plus minus 4 milligrams.
Probability distribution sample. In situation where we cannot study the whole population or when we cannot predict the mathematical form of a population, probability distribution, we must deduce the distribution from a limited sampling of its members. To better understand the probability distribution sample, let me give you some examples. We are going to flip a coins 2 times, so let's deduce the outcome of the coins. It can be tail and head and head and head, head and tail and tail and tail. Sample distribution and central limit theorem. According to this theorem, in system subject to a variety of indeterminate errors, the distribution of result will approximately normal. The central limit theorem holds true even if the individual sources of indeterminate error are not normally distributed. To further understand this, let's take a look for an example. The data in the table 4.12 are best displayed as histogram, in which the frequency of occurrence for equal intervals of data is plotted versus the midpoint of each interval. As you can see in the histogram, it shows the 100 penny with different weight in grams. But what does this graph meant to understand the central limit theorem? Even though it is unequally distributed, we are assuming it is a normal distribution. So, central limit theory, it allows us to safely assume that sampling distribution of the mean will be normal in most cases, even though the population distribution are unequally distributed.
Degrees of freedom. Unlike the population variance, the variance of a sample includes the term n minus 1 in the denomination, where n is the size of the sample that s to the power of 2 is equals to sigma index to the power of n is equals to 1, open parenthesis x index minus over x, close parenthesis to the power of 2 over n minus 1. In the case of population, the degrees of freedom is always equal to the total number of members and in the population. For example, S variance, however, substituting x for prefix multiplier removes a degree of freedom from the calculation. That is, if there are n members in the sample, the value of the nth member can always be deduced from the remaining n minus 1 members and negative x. Another example, if we have a sample with 5 members and we know that 4 of the members are 1, 2, 3, and 4 and that the mean is 3, then the fifth member of the sample must be open parenthesis x minus xn close parenthesis minus x1 minus x2 minus x3 minus x4 is equals to open parenthesis 3 times 5 close parenthesis minus 1 minus 2 minus 3 minus 4 is equals to 5.
Hello everyone, now we will discuss the step-by-step what the confidence interval is, what it is used for, and how to solve its problem. So let's get started. What is confidence interval? So it is a specific interval, the estimate of a parameter determined by using data obtained from a sample. Also, in statistics, it is the parameters of the population are often estimated based on a sample. So therefore, on the one hand, you have the population, but since in most cases, you cannot serve the entire population or you don't have data about the entire population, so you draw a sample. Now, the sample is used to estimate a parameter of the population. So the parameters that are estimated are, for example, is the mean or the variance. Here's an example in 4.15. What is the 95% confidence interval for the data in table 4.1? So if you are wondering, you can see the data in the first slide PowerPoint of the reporting. So here is the solution. The mean and standard deviation for this sample are respectively 3.117 grams and 0.51 grams. Since the sample consists of 7 measurements, there are 6 degrees of freedom. The value of T from table 4.14 is equivalent to 2.45. Substituting into equation 4.13 gives, so here is the equation. Population mean is equals to sample mean plus minus DTS, and then you have to divide it to the square root of the given number. So here is the example. 3.117 grams plus minus the 2.45 times the 0.051 grams, and then you have to divide it to the square root of 7. So the total of it is 3.117 plus minus the 0.047 grams. So thus, there is a 95% probability that the population's mean is between 3.070 and 3.164 grams. Lastly, if you are wondering why the results is between 3.070 and 3.164 grams, so here is why. So if you plus and minus the 3.117 grams of the 0.047 grams, it is equals to 3.070 grams and 3.164 grams. So I think that's all. Thank you.
There is a temptation when analyzing the data to plug numbers into an equation, carry out the calculation, and report the result. There is never a good idea, and you should develop the habit of constantly reviewing and evaluating your data. For example, if analyzing 5 samples gives an analyte's mean concentration as 0.67 ppm with a standard deviation of 0.64 ppm, then the 95% confidence interval is this. This confidence interval states that the analyte's true concentration lies within the range of negative 0.16 ppm to 1.44 ppm, including a negative concentration within the confidence interval should lead you to reevaluate your data or conclusions. On further investigation, your data may show that the standard deviation is larger than expected, making the confidence interval too broad. Or you may conclude that the analyte's concentration is too small to detect accurately. A second example is also informative. When samples are obtained from a normally distributed population, their values must be random. If results for several samples show a regular pattern or trend, then the samples cannot be normally distributed. This may reflect the fact that the underlying population is not normally distributed, or it may indicate the presence of a time-independent determinate error. For example, if we randomly select 20 pennies and find the mass of each penny exceeds that of the preceding penny, we might suspect that the balance on which the pennies are being weighed is drifting out of calibration.